In this example, we're going to use the integral test to determine whether the following series converges or diverges. Remember, the integral test basically puts the question of convergence or divergence onto an improper integral. But in order to use the integral test, we must show that the series function satisfies three criteria. So that's what we're going to start now. So for this particular problem, the series function is, well, it's going to be the function inside of our series, but basically with the n's replaced by x's. So we're thinking of x as a real variable that's more or less continuous. And we're thinking about this starting from, well, x equals 1 and going towards infinity. And that's because our series is starting off at n equals 1. So what we need to do is test three criteria. The first is whether or not this series or function f of x is always positive, again, on the interval we care about for x values greater than 1. And in this case, any x value we put into this that's greater than 1 is going to result in a positive number inside this function. We have positive coming from 3 times any positive number. And whenever we evaluate an exponential, at any x value, that's always going to be a positive quantity. So multiplying two positive things together results in a positive thing. The next thing we need to worry about is whether or not this function is continuous. Really what we're asking for here is, does it have any holes, or do we get any divide by zeros anywhere? And in this case, well, an exponential function, even a decaying exponential function, is always a positive thing. And 3 times any positive x value, that's also going to be positive as well. We're never going to get a divide by 0 anywhere inside of this product of 3x and this exponential function. So it's continuous. Yes, it is. The next thing is, well, this is where we're going to do a little bit of work. We need to show that this function is decreasing from for x values greater than 1. Or really, we need to show that it's always decreasing, at least from some finite x value onwards. So, okay, so we're going to start with our function. F of x is 3x times e to the minus 4x squared. And we're going to take a derivative of this and show that the derivative is always negative for x values greater than 1. So let's take a derivative of this function. And now we have the product of two things, that 3x and that exponential. So we get to do a little bit of product rule. So first, differentiating the 3x, we get a 3. We leave that second function alone, the exponential. And then we add to it the opposite. We leave the 3x alone, and then we differentiate that exponential. And whenever we differentiate an exponential, we get back, well, the original exponential there, but then we also get to differentiate by what's upstairs in that exponential, which in this case, when we differentiate the minus 4x squared, we will get a factor of minus 8 times x. So if we look at this derivative, we see that there's two terms that are the same in e, or there's a term that's the same in e to the exponential. So I'm just going to pull that exponential out in front. So we have this as e to the minus 4x squared. Now times the quantity, 3, and that's coming from the 3 in the first term. And then we add to that, or subtract, this product, because 3x times 8x is minus 24x. So we have 3 minus 24x. And now when we look at this, we want this to be negative for x values greater than 1. And well, we already talked about that this exponential, this thing is always going to be positive for any x value. So the only way that this thing's going to be negative is from this second term. And when we're thinking about x values greater than 1, if we put any x value greater than 1 into this thing, well, this minus 24x is going to cause this entire thing to be negative. So in this way, we can say that this quantity, or this first derivative, is always going to be negative for x values greater than 1. And again, that's because when we look at the 3 minus 24x, that is always going to be negative for x values greater than 1. So we also have this function is decreasing. So once we've shown that our function f of x satisfies those three criteria, we can proceed with the integral test. In the integral test, again, it puts the question of convergence or divergence onto an improper integral. Basically, the improper integral version of our series function that we see. If this improper integral is a finite number or converges, the series converges. If the improper integral is infinite, well, or the improper integral is divergent, then the series diverges. So let's look at that now. So looking at this improper integral, again, we have the integral of our series function, which in this case is 3x e to the minus 4x squared. We integrate with respect to dx. And, well, we're integrating from x equals 1. And the reason we're integrating from x equals 1 is if we go back to our series starts at n equals 1. And moreover, we saw that for x equals or x values greater than 1, our series satisfies all three of those criteria. So that's where we'll start the lower bound of integration. And we integrate all the way to infinity. Now, this is an improper integral because we're integrating up to infinity. So infinity is an integration bound. And the first thing we do with improper integrals is we introduce a limit to help us take care of that funky bound. So in this case, we're going from x equals 1 again, all the way to c once we introduce the limit as c goes to infinity. And we still have the same integrand as we did before. And now that we've introduced that limit, we proceed with the integral the way we normally would, using whatever integration technique we find appropriate. So we ask ourselves, U sub, integration by parts, trig sub, is a trig identity going to be helpful here? Are we doing partial fractions? So if we're looking at this particular example, we might notice that inside of this exponential, that minus 4x squared, well, its derivative is going to be related to an x to the first. And why that's useful is, well, if that derivative of 4x squared is related to an x to the first, we see that type of term sitting there in the integral. So we'll be able to cancel those x's through the u substitution. So let's go ahead and try that. So we'll let u equal minus 4x squared. So the derivative of u then is equal to minus 8x, which when we solve for du and dx, that relationship, we will get that du over minus 8x is equal to dx. So let's substitute all of this into the integral. And again, that limit's going to come along for the ride. We still have the same integration bounds. We haven't changed those. So from x equals 1 to c, we have that 3x that's still there. But now we have an exponential e to the u, and we multiply by what we found for dx in terms of du, which in this case is du all over minus 8x. So what we'll see happen right here is that the x's will cancel out. So the integral that we're considering is the following integral. We still have the limit as c goes to infinity from x equals 1 to c of 3 over minus 8. And again, we could take that constant and put it in front of the integral if we want, times e to the u du. So again, we can move that constant factor of 3 over 8 into this integral, or outside the integral, because it's just a constant. And now we just have the integral of e to the u left to do. So the antiderivative of e to the u, well, that's a nice one for us. That's just e to the u. So we have the limit as c goes to infinity of minus 3 over 8 times the antiderivative, which is e to the u. And we're evaluating that from x equals 1 all the way to c. So remember, before we actually plug in those bounds, we need to replace u with what it originally was in terms of x. So we can do that now. So we have the limit as c goes to infinity of minus 3 over 8. And u was originally minus 4x squared. So we can write that as e to the minus 4x squared. And now we're at the point in which we can plug in those integration bounds from x equals 1 to c. So let's go ahead and do that now. Plugging in the first bound, we have e to the minus 4 c squared. And we subtract the lower bound, which is e to the minus 4 times 1 squared, which is just e to the minus 4. And again, this second term, this is just some finite number. And the reason I'm pointing that out is because the brunt of whether or not this improper integral converges or diverges will depend on the terms with the c on them in which the limit is applied. So if we rewrite this limit, just doing a little bit of algebra, this limit's going to stay the same as c goes to infinity of 3 over 8. I'm just going to rewrite this exponential function since it has the e to the minus 4c squared. This is equivalent to 1 over e to the 4c squared minus, well, we could write that as well, 1 over e to the 4. And the reason why I'm writing this is we know that exponential functions themselves, as x goes to infinity, exponential functions go to infinity. Again, if we're drawing exponential functions, they look like the following, our little sketch on the right. This would be the sketch of e to the x as x goes to infinity. So what that means is 1 over an exponential that's growing very large. This quantity, or this overall fraction in this limit, what this looks like to me is a 1 over infinity type situation. And when we have a 1 over infinity, that's a really, really small type number. So this whole quantity actually goes to 0 in that limit as c goes to infinity. So what this improper integral is equal to is minus 3 over 8 times a minus 1 over e to the 4, which is equal to a 3 over 8 e to the 4, since the minus signs cancel out. And now, since this is a finite number, the improper integral is convergent, which tells us that the series is also convergent. And again, the reason why it does this is since the improper integral converges, by the integral test, our series also converges. Now, the one thing I just want to make a note of is just to say, even though the improper integral converged to 3 over 8 e to the 4, that does not mean our series equals that value. So I'll just make a little note of this. All we know is the series converges. (3n e to the minus 4n squared), all we know is this converges. It's very likely that this does not equal 3 over 8 e to the 4th. All we know at this point is that series is convergent, but we don't know what that series adds up to.